All right, let's get started with 7.3. In this one, we're going to look at pH in a little bit more detail and some titrations. Okay, so let's get started. So let's get started looking at the pH and what it actually means. P in pH stands for power of, and H is hydrogen. And it is basically a mathematical determination of the amount of hydrogen ions that are in the solution. So if we take a look over here, let's find a pen and circle it in red. If we look right here, there's a formula that gives us the pH, which is equal to the negative log of the molar hydrogen ion concentration. Now, we know what molarity is, and you can see that it's in these little brackets. Let's get a eraser so you can really see. You see these little brackets here? Those brackets mean molar concentration. So if we take the negative log of the molar concentration of hydrogen, we will get the pH. And it's really based on a logarithmic scale that goes from 0 down here all the way up to 14 up here, with 7 being neutral. And when the pH is equal to 7, that means the hydrogen ion concentration is equal to 1 times 10 to the negative 7. I know that gets into a little bit more detail than you actually need to know, so let's take a step back and let's just look at this, okay? If I have a pH, I'll write it down here, that is equal to 1, then my molar concentration, the amount of hydrogens that I have dissolved in 1 liter of solution, is 0.1, okay? So if I took negative log of the 0.1, I would end up with 1. Go ahead and you can try my math and make sure that I'm right. Okay. If I wanted to find the pH of something that has a pH of 2, or if something has a pH of 2, then my molar concentration, the concentration of the hydrogen ions, is going to be 0.01. So if I took the negative log of 0.01, I should get a pH of 2. Now look, this right here, color blue, this right here is 10 times greater than this right here. This is 1/10 and this is 1/100th. So there's a 10-fold increase in concentration of hydrogen ions in a pH of 1 than there is in a pH of 2. All right, I'm going to just go to the next slide and maybe we'll make this a little bit easier for you to understand. All right, let's take a look at this. I just made this really quick pH scale with 0 all the way down here and 1. Let's see, I need a pen. 1, 2, 3, 4, 5, 6, 7 being neutral. Now when you have neutral, remember the hydrogen ions are equal to the hydroxide ions. And then 8, 9, 10, 11, 12, 13, and 14. Down here we have our acids, and up here we have our bases. Okay? If I have a pH of 1, I'll highlight that right there, and I move to a pH of 2, so I'm going in this direction, I am getting less acidic, which means the amount of hydrogen ions is going to decrease. And it is going to decrease by a factor of 10. So every time we jump from a pH of one number to a pH of the next number, I'm changing by a factor of 10. So right here, I have a pH of 1, which means I have 0.1 molar hydrogen ion concentration. And right here, where I have a pH of 2, I have 0.01 molar hydrogen ion concentration. So I have a 10-fold decrease in the amount of hydrogen ions as I move to the right. If I make it a pH of 3, so if I come here now, so I went from a 1 to a 2 and then now to a 3. Whoops, let's go back to a red pen. Okay, I am moving 2 spaces. I'm going from a pH of 1 to a pH of 3. Every time I move, I am changing by a factor of 10. So first figure out what's happening. I'm getting less acidic, so my amount of hydrogens or hydronium ions, remember this down here is going to have the most hydrogen ions, and up here I'm going to have the least hydrogen ions. And every time I move by a factor of 10. So if I go from 1 to 3, I am actually going to decrease the amount of hydrogen ions by 100-fold, right? 10 times 10. Every time you move from one number to the next, we are changing by a factor of 10. And that's because we are working in a negative log base 10 system. Okay? All right, now, what happens if I'm going from a pH of 11 to a pH of 10? What happens if I'm going in this direction? Am I becoming more or less acidic? I'm becoming more acidic because I'm going from 11 to 10. If that's the case, how much more acidic is a pH of 10 compared to a pH of 11? Well, it's 10 times more acidic because every jump is by a factor of 10. And if I'm becoming more acidic, what's happening to the amount of hydrogen or hydronium ions? It's increasing. So if I'm going to the left, the amount of H plus ions is increasing. I'm just writing that down for you. If I'm going from the left to the right, like I did over here, the amount of hydrogen ions is decreasing. And then you just have to figure out, what is it decreasing by? Is it decreasing by a factor of 10? Or if it's doing 2 jumps, is it decreasing by a factor of 100? Same thing here. If you're at 11 and you go to 10, you are increasing the amount of hydrogen ions by a factor of 10. But if you're going from 11 to 9, you're increasing the amount of hydrogen ions by a factor of 100. If you were going from 11 to 8, 1, 2, 3 jumps, you're increasing the amount of hydrogen ions by a factor of 1,000. 10 times 10 times 10. All right, so what I did was I just grabbed this slide again so we can see how this is working. And we'll just recap here. pH is a log scale. It's a log base 10 scale. Each number changes a tenfold. You're increasing or decreasing by a factor of 10 for every number. As you go to the right, that's why this arrow is going to the right, your hydrogen ions are going to decrease and your OH ions are going to increase. Remember, as we get closer to the 7 mark, hydrogens and hydroxides are going to be equal to each other. So as you decrease the amount of hydrogen ions, your OHs are going to increase, and that's going to the right. If you were going to the left, let's change the color now. If we were going this way, what's going to happen to the amount of hydrogen ions? You're getting more acidic, so it's going to increase. You're going to have more H's than you have OHs, so your OHs are going to decrease. And in that case, your pH is going to decrease. And here you have, if the pH is changing from 4 to 8. So let's think about what's happening here. We're going from 4 and we're going up to 8. So we're going to the right. My hydrogen ion concentration is going to, that's right, it's going to decrease because I'm going from 4 to 8. Remember, down here on the left side, down here, I have the most hydrogens. And up here, I have the least hydrogens. So what is it going to decrease by? Well, we're doing 4 jumps, 4 to 5, 5 to 6, 6 to 7, and 7 to 8. And every one of these jumps is times 10. I'm running out of room here. Times 10, there's 4 of them. So 10 times 10 times 10 times 10 gives you a 10,000-fold decrease in hydrogen concentration. And that's why we have this down here. 10,000-fold change, decrease in hydrogen. Okay, so I hope that makes it a little bit easier for you to understand how the pH scale works. This big fancy equation up here in the New York State Regents doesn't ask us to calculate it, but what they will do is they will give you something, let me go to another page and I'll show you. All right, they will give you something that looks like this, 1 times 10 to the negative fifth. That right there, that number, let's highlight it, will always be your pH, okay? Because this 1 times 10 to the negative fifth is really telling us that we have it's not a pen, 0.00001 molar hydrogen ion concentration, which means, look, 1, 2, 3, 4, 5. 1 times 10 to the negative fifth. And if I plug that number, negative log of 0.00001, into my calculator, you will end up with 5. So magic trick is to look at this number, this exponent number, and as long as that number, 1 times 10 to the negative fifth, is talking about how many hydrogen ions you have, that is going to give you the pH. Okay? So they could give it to you two ways. They could do 0.001 hydrogen ion concentration. They'll put it in brackets like that, and they'll say, what's the pH? Then you're going to say 3. Or they could do 0.00001 hydrogen ion concentration. That would be a pH of 5. Okay, two examples. Or 1 times 10 to the negative 3, or 1 times 10 to the negative 5. And these numbers are the pH. pH, pH. Yay. Okay. All right, let's see what we got next. All right, so now we get to talk in a little bit more detail about titrations. Okay, we've seen these questions before. I did them in the last unit when we did dilutions, but now we can look and see what they mean in terms of acids and bases. And you can think of, remember how I told you that, whoops, that's not a pen. This right here would be like before and this is after, okay? Well, you can think of it as acids and bases as well. And we're going to do a titration. Titration means that the number of H pluses and the number of OHs are going to be the same. So let's go and draw on the next page. There you go. Let's say we have a flask. I'll make it a beaker because I can't draw a flask. You know that. Okay. And in that flask, we have a bunch of H pluses. I'll draw 4 of them. Okay. So this is an acidic solution. We've got a lot of H pluses floating around in there. There might be some water in here, but that's H's and OH's. They're neutral. We don't care about them. We're just looking at the excess hydrogen ions. If I start adding a base to this, let's say we start adding some NaOH. That NaOH is essentially adding NAs and OH minuses, right? So we're going to start dropping some NAs. The NAs do nothing. They're going to form salts in here. And then the OHs are going to come in. Let's make them red. And they're going to start joining up with these H pluses, making waters. They're going to do this. H plus OH minus is going to form HOH, which is water. And we're going to start neutralizing that solution. Because originally it was acidic, you had lots of H pluses floating around, but now you have added the OHs so that those H pluses were neutralized. It's a neutralization reaction. Well, we want to know when that happens, and you can do that with this formula. The molarity of your acid, okay, that's the strength of your acid, times the volume of your acid, has to be equal to the molarity of your base times the volume of your base. Okay, or before and after, like we did with dilutions and neutralizations. Okay, so this molarity, if you recall, molarity is moles over liters, and volume is liters. Let's write it out. Liters are going to cancel, so you're going to have the moles of H plus equal to molarity over liters times liters is going to be the moles of your OH, because the bases are your OH. And when the amount of your H pluses and the amount of your OHs are equal to each other, voila, you have a neutral solution. So that's basically what this is doing. It's telling you at what point are you going to have equal numbers of hydrogens and hydroxides. Now we do run into a little itty bitty problem. Sometimes when we neutralize things, it doesn't work out as beautifully as we would like. So let's say we start with hydrochloric acid and sodium hydroxide, and we end up with HOH, H and OH, that's your water, and sodium and chlorine, that's going to be your salt. Oops, it turned out to be red. Okay? Because every time we neutralize something, we end up with an acid plus a base yielding water and salt. It doesn't have to be sodium chloride, it could be any salt, but that's what generally happens when you neutralize something. You end up with this water, which is neutral, and salts, which are mostly neutral. Okay? We're not going to get into that right now. But what happens if I add an acid that has 2 hydrogens on it and a hydroxide, a sodium hydroxide? Okay? You have a 2-to-1 ratio here. So every time you add the H2SO4, you get twice as many hydrogens as you do hydroxides. So we have to do a little trick. Let's get this out of our way. And the trick requires you to modify the MAVA formula. So I'll just write it here for you so you can see. This is not on your reference tables, but you do need to know it. So if they give you a neutralization reaction, and I was really careful, try not to give these to you before, but you have to look at the acid and see how many hydrogens are going to break off of that acid. And so we're going to multiply the acid side, the A side, by the number of H plus ions in the acid. And we're going to multiply the base side, the B side, by the number of OH ions in the base. Usually this is 1-to-1. Like when we had this up here, we had one H and one OH. But if they're not the same, you have to modify your formula. Okay, so we're going to practice 1 or 2 of those and see how that works. So I went and I grabbed a few questions, and I'm just going to go through them really quick, and hopefully this video is not getting too long. But let's take a look at this one. This one says that you have, which equation represents neutralization? Now, neutralization means to make something neutral. So you need an acid plus a base giving you salt and water. We look at the first choice. We have a metal and a non-metal, and we got this salt of some sort, right? There's no water being produced. So that is not going to be our neutralization reaction. In the next one, we have a metal and a non-metal giving us a salt as well. So that's not a neutralization reaction. Look at this right here, KOH. Is that an acid, a base, or a salt? Well, it's got a metal in it. That K is a metal, and that OH is a hydroxide ion. So that's going to be our base. Oops. And then let's look at the next one. H2SO4 starts with an H. It's a ternary acid, It's on table K if you're confused. And so that's going to be our acid. And if you have a base and an acid, you end up with a salt, double replacement reaction, and water. So there's my neutralization reaction. Now in this question, it's asking what type of reaction occurs when an H plus and an OH ion get together. Well, if we have H, which is the acid, and the OH, which is from the base, and we end up making water, we end up with something that is neutral. And that is a very special type of reaction called a neutralization reaction. Bam, done. Moving on to the next one. Number 11, or slide 11. In a titration, okay, so we learned about this in the last unit. If it says the word titration, what formula are you writing down? Without even thinking or without even going any further, I'm going to write my MAVA formula, MAVUB, because it told me titration. Then I'm going to look and I'm going to see I have 5 milliliters of a 2 molar sodium hydroxide. This is a base. That's a base right there. So I'm going to put that on this side of the equation. My volume is 5 milliliters. My molarity was 2. Okay? There's one OH ion in this sodium hydroxide, so I'm going to multiply that side by 1. Now, this says neutralizes 10 milliliters of a hydrochloric acid. This is your acid. You know that because it starts with an H, and there's your nonmetal. We want to know what the molarity is. They told us they gave us 10 milliliters. How many hydrogens are in that acid? 1. So because these were 1 and 1, and this is what I've been giving you, hopefully that 1 and 1, it doesn't affect the reaction at all. So we're going to end up with 10x equals 10, x equals 1 molar hydrochloric acid. And we're good to go. All right, let's move on. Okay, now in this question, it says information related to a titration. Titration, ding, 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 ding. You should be thinking to yourself, write down your MAVA formula. MAVUB. Okay, the molarity of your acid. Let's go and see. And they give us our acid plus our base yields a salt and water. That's a classic neutralization reaction, right? They tell us the volume of that acid is 12. So the volume is 12. The concentration of that H2SO4 we don't know. So that's the molarity. So we don't know that. Now, how many H's are in this acid? There are 2. So this side of the equation needs to be multiplied by 2. The volume of the KOH, which is the base, is 36 milliliters. The molarity of the KOH, concentration is molarity, is 0.16. And how many OHs are in there? Only 1. Okay, so now we'll do our math. 24x equals 5.76. That's 0.16 times 36. And then I'm going to divide both sides by 24 to get rid of that 24. And x is going to equal 0.24 molar. So my answer is right here. Okay?